Hello and welcome. This is Mouse Gunner, and in this video I'm going to talk about short recoil operated systems in firearms. I'm going to do something a little bit unique compared to my previous videos on different operating systems in firearms, and then I'm going to do a little bit of a walkthrough history with the short recoil operated system and how it developed over time. But before I get into talking about my first example here, the Maxim gun, which is the very beginnings of the short recoil operated system, and the short recoil operating system overall, I am going to talk about something that's very important when we're talking about any of the operating systems, and that is the gas pressures that exist in the chamber. They need to be at a lower, safer level before extraction can begin to be considered a effective design. To explain the importance of this, I'm going to first have to explain what happens when a cartridge is fired. So you're going to have a striker or firing pin that's going to come in and strike the base of the cartridge case. Within that base is a primer, and as that primer is struck, it's going to ignite, burning the propellant which is found within the cartridge case. As this propellant burns, it's going to build up gas pressure. This gas pressure is going to expand out, pushing the bullet down the barrel. But it does have another side effect. As that pressure builds up, it's also going to push out up against the cartridge wall or case wall, and it's going to push it up in the direction of the chamber wall. Now this is a good thing because it creates a gas seal as those two elements are pressed together, preventing any of the gas from escaping out into the rest of the action. The problem with those forces pushing on the case walls is that if the gas pressure is too high during extraction, the period when the cartridge is being removed from the chamber, the pressure pushing out on the case walls can cause the parts of the case no longer supported by the chamber to bulge, and in extreme cases even rupture, possibly dangerously so. With that basic consideration of all operating systems explained, let's now talk about the basic attributes of the short recoil operated system. Now I'm going to show a number of examples in this video of the different variations of a short recoil operated system. There are many different ways to achieve the same results, but there are two main basic tenets of what a short recoil operated system is. First off is that it's a lock breech design, which means that the barrel and the bolt or slide are locked together. It is how the bolt and barrel unlock from each other. It is the main differentiation of the different variants of a short recoil operated system. Now the Maxim gun is a toggle lock variation of the short recoil operated system, and key to a toggle lock design is a knee joint, which we can find right here on the Maxim gun. So pay close attention to this knee joint as I go through the operation of the firearm. Now, starting off from the beginning, we already have the trigger pressed in, which is going to activate this trigger bar, which is also going to act upon a sear. Now, I'm not going to go over the exact specific details of how the Maxim gun works. Instead, I'm just going to focus on the short recoil elements of the firearm. But with that sear being tripped by the trigger bar, it drops our hammer, which we can see moving right there. That's going to strike our firing pin, igniting our cartridge. And with the ignition of our cartridge, we're going to begin our recoil impulse. And I'm going to zoom out here a little bit so you can see the barrel. So starting off from the beginning, keeping a close eye on the barrel here, you're going to see a little bit of a slight movement as it begins to recoil. The bolt and the barrel will travel together a very short distance, and then we have the bending of the knee joint. As the knee joint bends, it's going to unlock the bolt from the barrel, and they will now start traveling separately. Now, the barrel will continue to travel a little bit to the rear, but not nearly the same distance that the bolt travels. And that is the second element or attribute of a short recoil operated system, in that the barrel and the bolt travel together a short distance, but at some point they unlock and then travel separately, the bolt traveling the full distance to the rear and the barrel only traveling a short relative distance to the rear, at least compared to the same travel that the bolt takes. And that is where you get the short recoil element of the name short recoil operated system. One interesting element of the Maxim design is how it feeds in new cartridges and extracts out old spent cartridge cases. And to demonstrate that, I'm going to bring the cycle of the action back to the beginning. And we can see that the bolt face moves up and down during the cycling of the action. And at this point, when the action is closed, we have this upper part of the bolt face in contact with the rear of a fresh cartridge within the belt. And as the bolt recoils, it's going to extract out that fresh cartridge from the belt. At the same time, it's also extracting out our spent cartridge case from the chamber. This lug here on the bolt face is going to come into contact with this spring here, which forces the bolt face down in line with the chamber. And as the bolt reaches the full extent of its rearward travel, the tension of the recoil spring, which you can't currently see because it's on the other side of the firearm, is going to bring that fresh cartridge into the chamber, and the old spent cartridge case is going to be fed into this tube down here. And then we have our action closing and locking. And our old spent cartridge case is going to be retained down in this tube until the action cycles again, at which point a spent cartridge case that is already retained in this tube will be pushed out by the next extracted spent cartridge case. As we see here, this old spent cartridge case is being pushed out the front of the tube. As this firearm doesn't have its own ejector, it uses spent cases to do that. So this old spent case is acting as the ejector on the previous spent case within this tube. And then that old spent case gets pushed out forward and can drop freely now that it's left the firearm. To bring the bolt face back up to the top so we can start the process all over again, we have this camming arm here, which is going to act upon this lug here that will push the bolt face back up. So we can see this happening right about now. So you see that camming arm pushing up on the bolt face, which brings it back up to the top. And that is a complete and full cycling of the action, feeding, extracting, and ejecting. Now let's talk about how the knee joint on the Maxim locks and unlocks the bolt from the barrel. And this works off of the principle that the knee joint in the straight position does not naturally want to bend under the energy of the recoil impulse, which is also pushing straight to the rear. Without some outside force acting upon the knee joint, making it bend, the bolt and barrel would just travel straight back together, and they would never unlock. And we wouldn't get the extraction of the spent cartridge case and the feeding in of a new round that we would need in a semi-automatic action. That outside force is provided to us by the camming action of the slope contour of the charging handle interacting with this rounded surface here. So as we cycle the action, the bolt initially starts traveling straight back to the rear. But as it travels to the rear, it also forces the charging handle back to the rear. And with that rearward motion, the charging handle contacts the rounded surface. And through camming action, it initiates the direction of the bending of the knee. As the charging handle is forced upward, it interacts with the joint to push it downward. And that's all we need out of the charging handle and its camming action, is just to start the direction of the bend. Because once the knee joint starts bending, the continued rearward force upon that knee joint is now going to force it down as it's no longer locked straight. And as that knee joint bends down, it pulls the bolt along with it, unlocking it from the barrel. And that's how the toggle lock design works. And if we come around to the other side, we can see how the recoil spring also interacts with this. Now, unlike a lot of other designs, the recoil spring is not compressed. Instead, it's pulled upon. And as it's spread apart, these links here are attached to an arm here, which also, if we go down on the X-ray, we can see has this hexagonal pin. Now, this pin is within the rear portion of this knee joint. And as the knee joint rotates, it too rotates upon this arm, twisting these links. And as these links get twisted around, it pulls on the recoil spring. And as the bolt reaches its rearward travel, the tension of that spring being pulled and then release, yanking the links back around. This causes a twisting motion in this arm, and as that arm is attached to the rear portion of the knee joint, it then twists it as well using that hexagonal surface of the pin to bring the knee joint around, bringing it back straight. And once we get fully closed, we can see and mirror the arm here twisting along with the knee joint. Now, there's one key element of the function of the Maxim gun that I haven't yet explained. I've gone over how the bolt moves and how the recoil spring works and how a number of the functions in the Maxim gun work. But the one thing I haven't addressed is that this being a short recoil operated system, it has a lock breech design, meaning that the bolt and barrel are locked together. And I haven't yet explained what makes that the case, what locks the bolt and barrel together and makes them travel together for a short distance. Well, it's this plate here, which is attached to the rear portion of the knee joint back here because of that pin that runs through to the knee joint from the recoil spring assembly. So that pin is coming through and intersecting this plate. So what happens as the knee joint travels straight back initially before it starts to bend is it's going to drive this plate back. Now, the importance of that is the fact that this plate is also attached to the barrel. So you see this circular cutout here? Well, if I bring back the x-ray a little bit, you'll see that that cutout is filled, and it's filled by the barrel. So there is a circular peg on the side of the barrel that fills in that hole. And you can see that the barrel also has a similar peg on the other side. So why is this lockup necessary? And that's because the energy of the recoil impulse is just going to push straight back up against the bolt. And naturally, only it would move to the rear. So we have to have some mechanism to pull the barrel along with the bolt to keep them together that short period of time that's required for a short recoil operated system. So if you watch the plate in the background, as the bolt travels to the rear, it's initially going to travel straight back to the rear, as we've discussed in the past. And when it's traveling straight back, the plate, which is attached to the barrel, pulling the barrel along, is going to travel the same relative distance, keeping the barrel and the bolt together. But once the knee joint starts to bend, because of that articulation of the knee joint, the bolt is going to continue to travel at the same rate to the rear. But the plate and the barrel are not, because most of the momentum of this bolt is being translated into this downward force into the knee joint, not straight back into the plate. So although the plate's going to continue to travel to the rear, not nearly the same distance that the bolt travels. And once the bolt comes back forward and the knee joint locks back into the straight position, the bolt and barrel are locked together again. The next variation of the short recoil operated system we're going to look at is that of the locking block design of the Mauser C96. Just as before, we're going to have the drop of the hammer, which is going to strike our firing pin. Our cartridge is ignited and fired. We have the beginning of our recoil, which initially the bolt and the barrel, which are locked together, will travel together. And then a short distance after that travel, the bolt will unlock from the barrel. Come the rest of the distance of the travel of the recoil, extracting and ejecting the spent cartridge. And then as it comes forward, it will feed in the new cartridge into the chamber, and the barrel and bolt will come forward, locking in place and ready for the next cycle of the action. So the main thing we're going to look at is how is this different from the way the Maxim works? More specifically, how does the bolt lock and unlock from the barrel? Or in this case, actually the slide, as the slide is directly connected to the barrel. And it does this by using this locking block right here. Now this locking block has two lugs on it, one here and one here, that match corresponding cutouts in the underside of the bolt. It also interacts with the slide, which you might be able to just make out with this lighter colored surface right here, butted right up against the locking block. So as we cycle the action, and we have the rearward travel of the bolt under the energy of the recoil impulse, initially, the bolt and slide are going to travel together. And this is because as the bolt travels to the rear, it's going to pull back on the locking block, which also exerts a force upon the slide. But as it pulls to the rear, the bolt also tries to pull the locking block to the rear, but the locking block is fixed into the frame, and it cannot travel straight back. So instead, it cams along a pin and drops down. Once it drops down, the slide and the bolt are free from each other, and the bolt will travel the rest of the distance, and the slide stops when it contacts a point in the frame that doesn't allow it to travel any further. The bolt then travels fully to the rear and then comes fully forward under the strength of the recoil spring. So how exactly does this camming work? Well, this is going to be a little bit hard to picture, as unfortunately the locking block is one part that I can't actually show you right now, but you might be able to just make out the outline of it. Now the locking block itself has a little arm on the end of it. This arm is going to match up with another arm with this piece here, which is pinned in place. Now this piece is also going to butt up against the plug of the recoil spring here. And we'll see how those interact with each other as we cycle the action. So as the bolt travels to the rear, it's going to start to pull on, which we can just make out, the locking block. By pulling on the locking block, it's going to also pull via this arm on the other matching arm. As it pulls on that arm, it's going to rotate this whole piece along the pin point, or along this pivot point, I guess I should say. And as it rotates, it's also going to cam along the locking block, which then drops low enough to come out of contact with the bolt, which we can see here. And as this piece rotates down, it also compresses this spring here, which also powers the hammer. And as our action cycles, it comes back around. Eventually, we see that as our bolt starts to come forward, it's starting to allow our locking block to also come up. And under the strength of the spring here, the locking block then rotates back up into alignment with the cutouts on the underside of the bolt. And there we have the operation of the locking block. So let's see that again with the locking block in view. So the bolt pulls back on our locking block. The locking block pivots down through the camming action. It's held in place here by the bolt, so it can't travel upward, even though this spring is trying to make it go upward. But eventually, as the action cycles back closed, the locking block starts to come back up through the force of the spring here. Now, I must admit that this animation isn't perfect, as you can actually see the locking block clipping through the surface of the bolt, but it does at least illustrate how the overall process works. And that's more or less the main difference. Everything else is more or less the same. The main tenets of a short recoil operated system, the fact that the barrel and bolt travel a short distance, everything is more or less the same. The main difference, outside of a lot of mechanical differences with how it feeds and extracts and things like that, but the main difference with a short recoil operated system in this case is how the bolt and barrel lock together, which is done by a locking block design. The next example we're going to look at is the Luger P08, which is a return of the toggle lock system. So the main thing we're going to look at is the different elements of the firearm that we recognize from before. So the first part we're going to want to look for is the knee joint, which is right here, right on the top here. Unlike the Maxim, it opens upward rather than downward, but otherwise more or less very similar in idea. And then the next thing we're going to look for is that outside force that causes the knee joint to bend. And this is again going to be a camming reaction. So there is a knob here on the knee joint, and it is going to come in contact with a slope surface here on the frame. So again, rounded surface coming in contact with a slope surface. And as the slide comes to the rear, the knob of the knee joint is going to strike the frame. This is going to start the upward motion of the bend of the knee. Once the knee bends, it doesn't want to stop bending until we've arrested the rearward motion of our bolt. And then the return of the recoil spring brings the bolt back forward and closes our knee joint. Let's go ahead and see the interaction of the recoil spring and how that works. So the recoil spring's right here, where you might find the trigger spring of a hammer-fired firearm, but as this is striker-fired, we have that space to use. This spring is going to have a number of interactions here. So first off, you have a pin here and the rear portion of the knee joint. This is attached to an arm, which in turn is hooked into another arm, which is in turn hooked into this, I'll say piston, for a lack of a better term, which as the slide recoils, it's going to pull back on this arm, which in turn pulls up on our piston, which is going to compress our recoil spring. And once we get to the rearward most travel, the recoil spring is then going to use the force of its tension from being compressed and push back down on our piston, which in turn is going to pull down on this arm, which is then going to pull down on the next arm. As that arm gets pulled downward, it's actually going to force the knee joint here to unbend itself and rotate down. And as it rotates down, it straightens and then locks in place. So it's a pretty complex system here of interactions, but one could argue simpler than the system of interactions found on the Maxim. The next example we're going to look at is the 1911, which is going to be our representative of a tilting barrel design. The tilting barrel design is what I consider a variation of the locking block design. The main difference being it's the barrel itself that functions as the locking piece, locking itself to the slide rather than a separate mechanical piece that locks the barrel and the slide together. To achieve this on the 1911, two lugs are cut out into the barrel. And these match two corresponding cutouts on the inner surface of the upper part of the slide. And it's this interconnection of the lugs and the cutouts that lock the barrel to the slide. So as we cycle the action, the rearward push of the energy of the recoil impulse is going to drive the slide and barrel back. And initially they travel together, but as the barrel travels to the rear, it starts to tilt downwards. And once it tilts downward enough, the connection between the cutouts in the slide and the lugs on the barrel break. And once this connection breaks, the barrel and the slide are unlocked from each other, and the slide will continue to travel to the rear. The barrel will stop at a point and no longer travel to the rear, but as the slide continues to travel to the rear, the rest of the distance of the recoil, it will extract and eject out the spent cartridge case, and once it reaches the full extent of the rearward travel, the compressed recoil spring will bring it back forward, dripping in a new cartridge into the chamber. And then once the slide comes into contact with the barrel, it will begin to push the barrel back forward. And as it gets pushed forward, it will then tilt back up, bringing the lugs back into contact with the cutouts in the slide, locking them back together. The barrel tilts downwards due to its interaction with this link here, known as the toggle link. The toggle link is attached directly to the barrel via this pin here, and to the frame via this pin here. As the barrel tries to travel rearward, it pulls the link along with it. But because the link is also attached by the other end to the frame, it cannot travel directly to the rear like the barrel wants to travel due to the limitations of its length. So instead, it pivots along the frame pin, bringing the barrel down as it travels to the rear. Eventually, the barrel stops due to impacting the frame and can no longer travel to the rear. This is more or less how the tilting barrel design in the 1911 works. It's very much a simplified design compared to the previous designs we've looked at. The next example we're going to look at is the Walther P38, and like the Mauser C96, it's another locking block design, and also like the Mauser C96, the locking block here is a separate piece from the barrel here and the slide, which you can see in silhouette. Unlike the Mauser C96, we have a different placement of that locking block. If you remember, the Mauser C96 had its locking block back here with a bolt. And the method of its lockup and unlocking is also a difference that we're going to mostly focus on. Let's start off by watching a cycle of the action. And we can see in that cycle that just like the Mauser C96, the locking block falls, unlocking the barrel and slide from each other so that they can travel separately. So let's take a look at how the lockup works. So you have the locking block here in between two parts of the barrel. So this is the barrel here, and we also have the barrel over here. And the locking block is fit in this cutout here in the barrel. Now, it's not actually directly attached. It just has this spring, which you can just see the end of, which is a flat spring that keeps tension on the locking block, keeping it held at this point. But this is not a firm attachment point. And it's this location of the locking block that more or less keeps it attached to or in contact with the barrel. And it's a cutout in the slide, which we can see here in the silhouette on either side of the locking block. Now, the more important one is this surface here, which we can see the locking block is butted right up against. So as the slide gets pushed back by the recoil impulse, it's going to take the barrel with it, more or less. So now let's take a look at how the unlocking occurs. So in its current position, the locking block is locking the barrel and slide together. And even as we see the locking block dropping here, the slide and barrel are going to remain locked together. And it's not until the locking block drops free of its connection point with the slide that the slide and the barrel are going to really break free of each other and travel separately. But what force is causing that locking block to drop? It's actually at the other end of the barrel. We have this pin here. And as the barrel is brought back, it contacts a point on the frame, which you really can't make out here very easily, but there is more or less a flat surface right here on the frame. And as the barrel travels backwards, it's going to push in on that pin. And as it pushes in on that pin, we're going to have an interaction where that pin pushes out the other side. Now, this is going to be a little bit easier to see if I x-ray down a little bit further. So here we have the pin, and currently it is out on the rear end of the barrel, sticking out. But as we bring that barrel back, it's going to get pushed in, and we can see that the other end of this pin is going to go in this groove cut in the locking block. This is going to cause the locking block to cam downwards. So as that pin gets pushed in, it's going to push down by sliding along this groove on the locking block. So it's more or less just the impact of the barrel on the frame that causes this to occur. Now let's see how the lockup is re-engaged. So as the slide comes back forward, it's going to contact the barrel, and then the recoil spring is going to continue to push that slide and pushing with it the barrel forward. And as the barrel gets pushed forward, we're going to have an interaction between the slope surface here on the locking block and a corresponding slope surface on the frame. And as the barrel is pushed forward, those two slope surfaces are going to slide along each other, and that's going to force the locking block to cam upwards as it slides along that surface until it comes back up and locks back in place with the slide and barrel. And as it comes up, if we come back down into that x-ray, it's also going to push the pin back out. So we can see as it goes up, that slope surface on the inside of the locking block is going to cam along that pin, pushing it back out so that it is again exposed. So the next time the action cycles, it can impact the frame again, pushing the locking block back down. Now, this is a very similar system to what is used later in the Beretta 92. The Beretta 92 more or less adapts the Walther P38 system. So it uses the same style of locking block. It also has a pin like we see on the Walther P38. So very similar implementation. So with the Beretta 92, you can use a lot of the same principles you're seeing here with the Walther P38. The next example we're going to look at is the CZ75, which is another tilting barrel design. Now, this being a tilting barrel design, it has a lot of similarities to the design of the 1911. First off, it has locking lugs in the top of the barrel that match up with corresponding cutouts in the top of the slide, locking the barrel and the slide together. But where it differs is how the barrel tilts. This is what is referred to as a Browning-style tilting barrel design, which is interesting considering that the 1911 and this style of tilting barrel were both invented by the same man, John Moses Browning. The main difference between the tilting barrel design found in the 1911 and that found in a Browning-style tilting barrel is how the barrel tilts. And in this example, we don't have the interaction of the barrel with a link that is attached to the frame. Instead, we have a camming action of the barrel along a pin that is attached to the frame. So as the slide and barrel travel to the rear, we will see that this cutout slot and the bottom part of the barrel moves along this pin. And as it cams along that slot, it is dropped down. And again, the lugs being dropped down breaks the connection between the slide and the barrel, unlocking them from each other. There are some variations of the Browning style tilting barrel design, and mostly that has to do with the shape of the camming surface. In some instances, the camming surface is cut to be more open here in the back, so this cut would continue out, and there would be no material here closing in the pin. And this is often done in cases where the surface that the barrel cams along is actually a fixed bar within the frame that isn't usually removed during disassembly. In the case of the CC75, this pin is removed during disassembly so that the barrel can easily be removed. But in other firearms, that isn't necessarily the case. So what they do is they just cut the barrel to be open here so that the barrel can be removed off the bar within the frame easily without any trouble. So that's the main difference. They both function exactly the same, just the barrel camming along a surface that's attached to the frame. It's just a matter of difference on how the firearm is disassembled. To wrap things up, I'm just going to quickly use the example of the Glock 19 to demonstrate a modern example of a tilting barrel design. So the main difference we have here is how the lockup occurs. So if you remember the CZ75, there were cutouts in the barrel that fit into corresponding cutouts in the slide. You don't see that here with the Glock. So how does the lockup occur? Well, it's still the same idea, but instead you have this part of the barrel that sticks up and interacts with the slide. So if we watch here, as the slide recoils, the barrel and the slide are going to stay locked together because of this surface. But just like with the CZ75, we're going to have a camming action here with the barrel and a bar that goes across the frame. So as that camming action occurs, the barrel is going to tilt downwards. And once this flat surface that protrudes on the top of the barrel has its contact broken from the lip of the slide there, the two will unlock from each other, and then the slide can travel the rest of the distance. That's the main difference. So it's the same idea, and I just wanted to showcase this. And as you can see, from what I was talking about with the CC75, the cut of the bottom end of the barrel here is a little bit different. It's more open-ended here so that it's easier to disassemble because you're not going to easily remove this piece here that the barrel cams along when you're doing disassembly. So the barrel's left open-ended like that so that you can remove it without having to remove this piece. Well, that wraps up the video. And the main purpose of this video was not only to showcase the different types of short recoil operated systems, but also to demonstrate that even if a firearm is of the same type, it doesn't necessarily operate exactly the same way. It uses a lot of the same principles, and all of these designs use the same basic tenets, and that is that it's a lock breech design, the barrel and slide are locked together, and at some point they're going to break that contact after a short distance, and then the slide will travel the rest of the distance after the barrel has stopped. So that is the main tenets of a short recoil operated system that all of them are going to follow, but exactly how they do that is going to differ. And even of the same type of short recoil operated system, let's say it's tilting barrel, you're going to have variations. For instance, you have the 1911, which is a tilting barrel design. You have the CZ75, which is a tilting barrel design. And you have the Glock 19 here, which is a tilting barrel design. And all three achieve that lockup and unlocking a little bit differently, but the principles are very much the same. In any case, I hope you guys have enjoyed the video. This is Mouse Gunner, signing out.